The trapezoidal rule, which is also commonly known as the trapezium rule. We have looked at finding the area under a curve using rectangles previously in methods. Instead of using rectangles as we did in methods, we'll use trapeziums, and we'll find that it gives a better approximation to the area. The approximate area under the curve is found by adding the area of all the trapeziums. We can see this example over here, where this has been split into trapeziums. You can see here, if you look closely, little bits of area that are under the curve but not under the trapezium. And I think over here, if we zoomed right in, the trapezium would actually be above the curve maybe, or maybe slightly below. But even so, those straight lines don't fit perfectly to the curve, and that's why it's an approximation. The area of a trapezium is given by area is h over 2, where h is the distance between the parallel sides. So if we have a trapezium, then what we might have are the parallel sides here and here. So these ones are parallel. And if this is straight across here, then that would be the h, the distance between those. And then we've got p plus q. So in this particular formula, we're using p and q as the lengths of the parallel sides. So h divided by 2, p plus q. We need right trapezoids, which means the parallel sides are at right angles to the base, as I drew in my diagram above, and as we can see in this diagram just here below. They're rotated 90 degrees, so the new base is actually h. So in the diagram below here, we called it delta x, but that's the h just there. As follows, and h is equal to delta x, which I just mentioned. So we've got a trapezoid here, just like the one above. P and Q, these two are the parallel sides. H is the distance between those parallel sides. It has to be the perpendicular distance between, and we have the formula as outlined above. And so if we apply it to this one here, the area for that trapezium would be delta x divided by 2, y0 plus y1. So if we now look back at this diagram up here, what would we get? So the areas would be delta x over 2, and then the first one would be y0 plus y1, and then for the second one we'd have delta x over 2, y1 plus y2, and then the next one would be delta x over 2, y2 plus y3, and we'd carry on, and the last one of those would be delta x over 2, y5 plus y6. Now what you'll notice there is there's a common factor of delta x over 2. The y0 only appears in one calculation, so does the y6. All the other lengths are there twice. So we would get that. And just generalizing that idea below here, the total area is given by A equals, there's the delta x over 2 that we've pulled out. The y0 and the last one, which was y6 in our example, would only appear once, but all the others would appear twice, the y1, the y2, all the way up to yn minus 1. This is the trapezium rule for n trapeziums. To find the delta x for the area from x equals a to x equals b, we just use delta x is b take away a divided by n. So a simple example there would be, let's say we went from 2 to 4 and we wanted to have 4 trapezia. we would just do 4 take away 2 divided by 4, and that would be 0.5, and that would be right, wouldn't it? Because we'd have one at 2.5, then one at 3, then one at 3.5, and altogether that would form 4 trapezia for us. We also need that y0 is f of a, y1 is f of a plus delta x, y2 is f of a plus 2 delta x, and so on. So here the height there would be f of 2, that's what we're saying, and the height here would be f of 2.5, which is 2 plus 0.5. We go up to yn, which is f of b, that's at the other end. Note, we get a better approximation if we take more trapezoids, up to a limit. I mean, all we can get at the end of the day is as close as you like to the true area, and you might get to a point where you can't tell the difference between the true area and your trapeziums to the accuracy of your calculator, but you can't actually get exact with all those straight lines, except in an infinitesimal case, which would be doing the actual integral. The more trapezoids we take, delta x will tend to 0. We can write, if the curve is above the x-axis, only between x equals a and x equals b. Otherwise, we have the same considerations that we had before, with some of the area above and some of the area below.